Okay, guys, so we're going to pick up where we left off in the last video. And here's just the example. When we say the law of capillaries, the idea here is that all of our, most of where our water and electrolyte levels that are going to occur within our interstitial fluid and plasma, they're going to happen between the capillary and the capillaries of our blood. So everybody remember those are the really, really tiny, little tiny capillaries that are at the end of either our veins or our arteries, depending on the situation. Okay. So the control mechanism between this, that's going to be your hydrostatic pressure and your osmotic pressure. Okay, so this is going to basically play a role. Along the other side, we have the interstitial fluid, hydrostatic and osmotic pressure. So the idea here is that depending on which way you want it to go, there will be an increase or a decrease in that pressure. And as so the way that you go from low to high, or from high to low. Sorry, from high to low. Remember, we always go from high to low because that takes the least amount of energy. Okay. So in this case, if we have so what we want to look at here, remember, this is our blood hydrostatic pressure, blood osmotic pressure. This is going to be our interstitial fluid hydrostatic pressure and our interstitial osmotic pressure. Okay. So we want to know here, the idea here is that they're equal. There's nothing that's going to move. When they're not equal, that's when it'll move. Now, if it's going to go from the blood to the IF, you have to have the blood hydrostatic pressure and the blood and the interstitial osmotic pressure be greater than the interstitial fluid hydrostatic pressure and the blood osmotic pressure. Okay, and again the opposite. So again, just looking at whichever one's greater. Again, going from high to low. So this indicates that we have a high amount of hydrostatic pressure here, which means that we almost essentially want to burst in the blood. And therefore, we want to go into the interstitial fluid in order to relieve that hydrostatic pressure. Okay? So some examples of when you have fluid imbalance. Edema is an example of this. So essentially, this is the large amount of fluid within the intercellular tissue spaces within the body. And it's basically going to allow for the electrolytes to be collected within one area. And it's kind of dangerous. This is when you get a lot of swelling. You might see that on TV. But the idea here, this is going to occur because of an increase in aldosterone. And therefore, it's going to increase capillary blood pressure. So it's going to essentially make it that the capillaries are going to almost close off a little bit. And that's because of the fact that you have essentially swelling in that area from the amount of fluid that is being maintained in the area that it's not supposed to be. Okay? Therefore, you're not going to have as many proteins that are going to be able to come through that area. So they're either going to be caught in different portions, whatever the case may be, but they're not going to be normally retained in the blood. And so that's going to be an issue that you have going forward. So essentially, it's like the people get like really, really swollen. If you ever seen someone with edema, you would know. Trust me, you would know. Okay. And this is an example of an edema. And also, too, like the biggest way you can tell too someone has edema is you can push like your fingers into it, like they're showing right here, and almost like they pop out. Again, it's just like, a waterbed essentially in your legs. It's the best way to kind of put it as an example. Okay. Okay. Okay, so some regulations that'll occur for this. Obviously, the plasma membrane plays a role in this. We want to make sure that we have the interstitial fluid or the intracellular fluid, that has a critical role in basically making sure that that is correct. And again, the interstitial fluid and the intercellular fluid, those hydrostatic and osmotic pressures or colloidal osmotic pressures, they're going to regulate the water transfer between the two. So it's going to be basically the idea here is that we have this plasma membrane that prevents it from, being like super, super, super easy for things to transfer back and forth. And it also allows for the proper composition of intercellular fluid. When we talk about this osmotic pressure and hydrostatic pressure, essentially what those are doing are preventing things from moving in one direction or another without there being a reason. Again, things would move just back and forth, back and forth, back and forth if there was no pressure. But because there's certain points, remember we talked about this in the last one, or in this one, we talked about how nothing happens if those hydrostatic and colloidal osmotic pressures were equal, okay, if they were all equal. So that's exactly what this is kind of stating here, is that in order for this transfer between the extracellular fluid and the intracellular fluid, this colloidal osmotic pressure plays a huge role in that. And essentially it regulates that along with the hydrostatic pressure. Okay? And the big thing behind that too as well, sometimes in order for this ion transport to occur, just want to kind of talk about this a little bit here, it might have to occur through active transportation. And in that case, what'll happen with that is you'll have, some type of pump that'll get either the sodium or the calcium to wherever you need to be. Okay? In addition, if we look at the cell membrane, proteins don't diffuse out of the cells very easily. That almost has to happen through active transport as well, because of the fact that they're just not going to go through the membrane. That membrane is tight, at least tightly enough composed that this doesn't happen as easily as it should. Okay. Okay, and that's pretty much it. Water will always move through osmosis. That's essentially diffusion, but water's special name for it. And sometimes too, if we have sodium attached within the water, it'll still diffuse through osmosis because water will be the major component, but sodium will be kind of like hanging around and riding along for the ride. Okay, so when we look at determining the number of sodium and potassium levels, again, that's going to be dependent upon the electrolyte balance that we're looking at, and that's going to be dependent on a various amount of factors, but the biggest ones are going to be the antidiuretic hormone and aldosterone, how much that's being secreted. So the antidiuretic hormone, this kind of allows for this extracellular fluid electrolyte concentration, basically by regulating the amount of water reabsorbed into the blood. So therefore it's going to either create a higher hydrostatic pressure in order to get things to move in, or a lower hydrostatic pressure if there's plenty to go. Basically higher means that we've reabsorbed more water, lower means we've let more water go through. And this is going to, aldosterone plays a role in the amount of sodium reabsorbed. So it plays a role in sodium reabsorption. Okay. And in general, when we look at this, kidneys are always usually going to be our regulators of sodium. Chloride's kind of going to be a little bit more of a role in potassium, because as much as sodium loves chloride, potassium loves chloride as well. And our body is basically going to be able to use the potassium better, because that plays a role in, your heart movement and things along those lines. So if you have potassium deficiency, this is what we call hypokalemia. I think that's how you say that. I'm not very good at saying any of these. Calcemia. My mom just told me that. She's a nurse, so she can tell me these things when I say things wrong now, guys. It's going to be seen in conditions, usually if you have starvation, if you have burns, some type of trauma or dehydration, you're going to see a lot of potassium deficiency. And these are just some fluid and electrolyte disorders. Again, you could have sodium imbalances or potassium imbalances, or you could have more fluid than necessary. So if you have any questions, please let me know. Okay.